Okay, welcome to Maths Linear Algebra Tutorial 4, question 9. We are given polynomials, and by now you know that polynomials can be considered as vectors as well. And this is the first polynomial, this is the second polynomial, and then the third one. And then we have three polynomials, and he asks us to, by inspection means check with our eyes, whether P1, P2, P3 are related. And it is obvious that P3 is equals to P1 plus P2. Now, once we have that, we realize that although we are given three vectors, P1, P2, P3, only two of them are independent. So the question now is, we're given three vectors, the span of these three vectors, meaning let's call this the vector space V, and we say V is spanned by these three vectors, means that V can be any alpha times P1 of T plus beta P2 of T plus gamma P3 of T. And then we have a vector space formed by any linear combination of these three vectors. And then he says that instead of using these three vectors, can I find a smaller set of vectors in V such that they still span V? So the key things is we want the smaller set to span V and are independent. So we realize that P1, P2, P3, although they span V, P3 is not independent. The key idea to answer this question is to understand these two words. What is a span and what is a basis? So we have done with question 9. Let's proceed. Tutorial 4, question 10. Here we are doing change of coordinate. Let's read the question first. He says that let's find an inverse matrix such that we can express this for this vector. So something strange is going on. He's saying that I want to express this vector in terms of the B coordinate. And what are now the elements of this X? So to figure that out, first understand X bracket B means we have X1 and then I put a B here. X2, I put a B here. To say that these vectors, although they are in R2, means that they are vectors of 2 dimensions. They're using the B coordinate, meaning that we must be expressing this as, for example, implying actually this is X1B, which is a scalar, multiplied by this is the first B coordinate, plus X2B multiplied by minus 4, 6. So the idea of saying that a vector expressed as a different coordinate, in here we are B, is saying that we are using these columns to represent how we move along the direction in B. All right, once we have understood that, then let's see how we can do this question. The idea is we put the B as a matrix, maybe 3 minus 5 here, minus 4 and 6. And remember that this is for column 1 and this is for column 2. And now I am going to multiply by the X value represented by the B coordinate. So this is the B coordinate matrix, and that is X of B using the B coordinate matrix. When I multiply B by XB, I will get the X. And now, actually he didn't write it for you, but this is the standard coordinate, meaning that this is a typical way we see the world. we are moving 2 steps along the x-axis. We are moving -6 steps along the y-axis. So once you have that, then he's asking you to find xb. Once you have this expression, it is actually obvious that this is b times xb equals to x standard. Therefore, since you want to find xb, what we do is we multiply the left-hand side and the right-hand side. We pre-multiply by b minus 1, the inverse of b. Therefore, b minus 1 times b, xb is equals to b minus 1 times the x standard. B minus 1 times b is the identity. So we have the identity times xb, and therefore we get what we want, which is xb. And now we have b minus 1. So let's go and solve for b minus 1 first. Let's write b first, not forgetting the inverse on the top right hand side. And then what is x standard is 2 and minus 6. So you should know how to perform the inverse of a 2 by 2 matrix. And then I will get the values here, which is minus 3, minus 2, minus 5 over 2, minus 3 over 2, and then 2 minus 6. And then we can get the answer as 6, 4. Now, please don't forget to write the b in the bottom to say that this is 6, 4 using the b coordinate. As a sanity check, what we always do is that we now go up and say that let us perform using 3 minus 4 minus 5, 6 multiplied by 6, 4. And what we want to do, this is b, this is xb, and therefore this should be the representation in the standard coordinate. And the answer is, we check it out, is equals to 2 minus 6, agreeing with what is given here. And we are done. Okay, now if you ever need some help, go to the Lay's book on page 241, 5th edition on Lay's book. He does a very good job in explaining. So I'll just show you the book now. And here, this is the page 241. Maybe we have a quick discussion of change of what is coordinate, the idea of coordinate. First, this guy views the world in this form. If we step one step along the first element of the b coordinate is using the green line. If we step one step along the second entry of the b coordinate, we are moving along this line, the red line. So this is how b looks at the world. What about c? This is how c looks at the world. For the second entry is along this red line, and along the first entry is along the green line. So C and D looks at the world completely differently. But the key interesting idea is that the origin remains the same point in the space. So in fact, if you take this figure on the right-hand side and put on top of the figure on the left-hand side, you will realize that the origin will match. Now, when the origin match, then the problem is, let's find where X is. Now, X will be exactly the same point when you put the two figures on top of each other. But in the B's world, he will describe it as X position is to move 3 positions along the first entry of the B coordinate and followed by 1 negative entry, one positive entry along the second coordinate or B. While the same position of X is described by 6 by 4. Let's see where the 6 by 4 is. So he is moving 6 directions along the first coordinate of C. So let's count 1, 2, 3, 4, 5, 6. And then he's moving 1, 2, 3, 4 position along the second coordinate of C. So that's why we have 6 and 4. Now please read this carefully. It took me a long time to figure this out because the notations are a little bit complex and you have a lot of other things going on here. Okay, so once we have understood this question, I can now actually jump to question number 16 first. Question number 10 and 16 are talking about the same kind of section, which is change of coordinate. Right, let's do this. So he asks you to find the change of coordinate matrix from A to B. So this is very similar to the examples we have just seen in Lay. On one side is a B coordinate system, the other side is the C coordinate system. Here we are doing A to B coordinate system. When we want you to use a coordinate system, we must tell you the basis associated with it. Remember, the basis means A1 means you're going to move along this direction A1 for the first entry of elements in the vector XA. So XA will be X1A, X2A, and X3A. The interesting thing is, if you do 1, 0, 0, you're actually saying I'm moving 1 times A1. And then if you have the second entry as 2, then plus 2 times A2. And then maybe I'll put the third entry as 4. Then it'll be plus 4 times A3. And that's the idea. Okay. So the coordinate system means that now I look at the elements in my vectors and multiply by the corresponding vectors in the basis. Okay, once you figured that out, then we know how to write the change of coordinate matrix. First, you write the given information out. The given information is basically telling you that A1 represented by B looks like this. That means transversing along A1 is equivalent to transversing 4 times B1 minus B2. That's what he's telling you. And then he gives you different information for A2 and A3. Now, when you take all these, you can realize that you can compactly represent it as a matrix because you put A1 represented in the B coordinate system as a column. So you're putting number 4 here, and you're putting -1 here. And since B3 is nothing, so in check is 0, B3, if you really want to be pedantic. So the first column of this matrix represent how A1 is going to, what you have to do in the B coordinate. Second one is -1, +1, +1. And the third one is 0, 1, -2. And this matrix, if we write all the information properly, this is A2 in the B coordinate, and this is A3 in the B coordinate. And this matrix is the change of coordinate from A to B. Okay, so this is the first answer. Now, how do we use it? We want to find XB, the representation in the B coordinate for this vector. For X is equals to 3A1 plus 4A2 plus A3. Now, he's telling you abstractly, but actually concretely he's saying, I am giving you a vector in the A coordinate. See, everything is in terms of A. So I'm actually writing this in the A coordinate, this vector. What are the elements of this vector? So the first element is 3. The second element is 4. The third element is 1. This is the representation of the point in the A coordinate. Let's go and find this guy. So the equation to use is x of b is equals to the change of coordinate matrix from A to B multiplied by x of A. And that's the idea. So we plug in all the values. Not forgetting all this information at the subscript so that we don't get ourselves confused. And I always like to write all this out so that I know that I am sending the vector in the A coordinate pre-multiplying by the change of coordinate from A to B, such that on the left-hand side, I will get something in B. And the answer is 822. Okay, so question number 10 and number 16 are related. Actually, they should be grouped side by side. Once you have done that, then we are okay. We're done with question 16. All right, so in fact, when you look at this question, he's asking you to understand the vocabulary associated with this. The first is dimension, subspace, R2, and span. So this question is very loaded. Yeah, he's assuming that you know a lot of things. So he's saying H is equals to the span of these three vectors. The span of these three vectors means any linear combination of these three vectors belong to the set. Now, when we talk about linear combinations, these are examples of linear combination, the scalar multiplied by the vector in the set. And you realize that, hey, I can create an infinite number of vectors. So H has infinite elements. Now, then he says that let's find the dimension. So what is a dimension? So the dimension is the word used with a vector space. So it's not dimension of something. So dimension of a vector space. And then, of course, a subspace is also a vector space. So he's not doing anything wrong here. So a dimension of a vector space. What is a dimension? It is the number of vectors in the basis for the subspace, for the vector space. So you realize that linear algebra is full of terminology, right? First, he tells you the dimension. You have to figure out the dimension is a subspace. Then, now he's asking you to figure out the basis. So just now in the previous question, we have already figured out what is a basis. Is the linearly independent vectors in the vector space. So we call it V, okay? The vector space V that spans V. So we are saying that go into V and find go and find independent vectors. And then go and make sure that they are independent. And after that, just count them. And that's it. That's the dimension. Now, actually, once he has given you R2, then he's basically saying the vector space V is any X and Y. And then you realize that to form this kind of vectors, R2, then the simplest one, the simplest basis is this. Now, he didn't give you that, he gave you this guy. And you realize that he's giving you extra things. So, so this is basically a trick question. Having said that, of course, he could have been very nasty. The question could have been very nasty because although he has given you 3 vectors here, you have to figure out whether they are independent or not. Okay, because we only need to count the number of independent vectors. So let's go and figure this out. All right, let's erase this now. And always to figure something out, we use this Gaussian elimination. So we let A equals to 2 minus 5 minus 4, 10 minus 3, 6. And we keep them as the columns. And then we perform reduced row echelon form or reduced echelon form, whichever is, reduced echelon form is easier. And then I get this. And then I count the number of pivots. And the answer is the number of pivots equals to 2, implying that I have 2 independent columns in A, 2 independent row in A is equals to the rank of A. And then the answer is that the rank of A is the dimension of the subspace. And the answer is the dimension. The question asks for the dimension of the subspace. So he's asking you actually the rank. 2. Okay. So although actually in this question you could answer it immediately, yeah, because all you need to do is you look at this, find how many of these vectors are independent, and then that's it. You just count them and then you just tell them the answer. All right, so I'm done with number 11. So it's tutorial 4, question 12 now. Here, null space of A and column space of A. So in this kind of tutorials, we have a lot of mechanical workings for such problems. So I was looking around, and then so I'm going to share with you some of the things that might be useful. Okay, so I have just uploaded something called tutorial 4 support just today. So the date should be changed to today. And in this tutorial support, again, the second slides will give you the Dropbox link to my work examples so you can see them, as well as this recording. So if I'm going to record this recording, it'll be found here. And then please go to this page number 5, and you will see a lot of examples on how to find the basis, null space, row space. Okay, so they do a very good. So I like Yotsumura. And then in Yotsumura, basically he gives you very concrete examples and then how to do all this one by one. Okay, so go through it and it will give you a lot of practice. So some student is asking me, what about practices? So these are many questions you can actually find in the internet, right? You can try this. So with that, we can now come back to our problems. Okay, the nice thing about this question is that actually when you're given a matrix, you are going to perform row echelon form, and then you can perform reduced row echelon form. We always like you to do reduced row echelon form. So if I have a question, is this matrix in row echelon form or reduced row echelon form or none of the above? The answer is actually it's only in row echelon form showing the 2 pivots. It is not in the reduced row echelon form because the number above the leading variable is not 0. So in reduced row echelon form, this number will be changed to be 0 through elementary row operation. Okay, so this is, but never mind, in row echelon form, the number of pivots still tell us a lot of things. The number of pivots is equals to 2, and then it tells us that this is the dimension. Again, what is the dimension? It is the number of bases in the vector space. So the dimension of the column space has 2 pivots. Sorry, the column space, the A matrix, it has, when it reduces, shows there's 2 pivots. Therefore, 2 of the columns are independent. Therefore, the dimension is equals to 2. So that's very easy once you've figured out. All right, what else? What about the null space? So there is the famous theorem called rank nullity theorem. What is rank? Rank is the number of independent row or column in A matrix. It's very strange. I mean, you'll realize that I've shown you this matrix A, and then we have figured out that there are two pivots. 2 pivots shows you that there are only two independent column as well as 2 independent row. The number of independent row and column are the same. Okay. What about nullity? Nullity is the dimension of the null space of A. So he's asking for the dimension of the null space of A, so he's asking for nullity. Okay, what does the rank nullity theorem says? It says that the rank plus the nullity is equals to the number of columns in A. And the answer of the number of columns in A is 4. The number of independent rows in A we have already figured out is 2. So the nullity or the dimension of the null space must be 2. And this is the answer. Okay. So again, although the math is trivial, then you have to have a lot of background to understand the rank nullity theorem. My math colleagues tells me that because we are only dealing with the matrix, we're actually dealing with matrix algebra, linear algebra. So the rank nullity theorem is applicable for vector space. That means it can be polynomials, it can be any kind of elements that we are talking about as vectors, not only matrices. So in here, we're talking about columns, number of rows and columns, because we are representing everything as a matrix. Okay, but in the mathematical world, it's a completely different idea, more abstract. All right, so I'm done with question number 12. Tutorial 4, question 13. So again, in fact, you realize that question 12 and 13 asking you to do almost the same thing, always asking you to find the dimension, counting the number of vectors in the vector space, null space, and then the row space. All right, let's start. A is equals to 3 by 8. So it has 3 rows and 8 columns. The rank of the matrix is given to us is equals to 3. So let's typically call this M. And let's call this N. So M by N is equals to 3 by 8, where M represents the number of rows and N represents the number of columns. Now, to figure this out, we use the rank nullity theorem. So we now write again it says the rank of A plus the dimension. The nullity means the dimension of the null space of A is equals to the number of columns, which is n. So what is he asking us to find? He's asking us to find this guy. Therefore, the dimension of the null space of A, which is the nullity, is equals to n, which is 8 minus what? 3. And the answer is 5. And we are done for the dimension of the null space of A. What about the dimension of this guy? All right, so let's, what is C of A? Equals to the column space of A. What is CAT? What it means is that you take A and now you transpose it. AT means you transpose A. So if I want to draw, so now I'm doing this guy. Yeah. So what is this? Oh, I'm trying to find the column space of this matrix. Okay. And how many columns are there? There are 3 columns. Are they independent? Yes. Why? Because the rank of A is equal to the number of independent columns as well as the independent rows. So the dimension of the column space of A is actually equals to, in this example, the rank of A, which is equals to 3. All right, so I'm done with number 13. So I guess, yeah, you guys have a question of number 14. So maybe I'll do it a little bit slower this time. So let's interpret the question first. The question says that I have a system of 5 equations and 6 unknowns. So I'm basically having 5 equations. So I will write as 1 equation, 2 equation, and 5 equation. How many variables are there? 1, 2, 3, up to 6 variables. I can represent this equation as the matrix A and the variables as x1, x2 until x6. And my right hand side, I can represent as B1, B2, and B. Okay, guys, be careful. I have 6 unknown. I have 1, 2, up to 5 equation. Therefore, my number of B should be B5. Okay, so that's the thing you must pick. All right. So basically now I can cast the problem as AX equals to B. And then the problem, of course, this is a 5 by 6. This is a 6 by 1. This guy is a 5 by 1. Now, what else? What other problems is he telling us? So he's telling us that the solution, what is the solution? Who's he talking about? Solution is X. So this is the solution. So solution is X. Homogeneous means the right hand side for homogeneous means this guy is equals to the 0 vector. The solution to the, such that the right hand side is 0 vector, has one non-zero solution. So he's saying that when we solve for this, when we solve above, for B equals to 0, X is what? all multiples of one non-zero solution. X is not the trivial solution, but some non-zero vector alpha. So this looks familiar. So if you guys want to think about it, he's basically asking you to find the null space of A. What is a null space of A? It is the set of X such that AX is equals to 0. And he's telling you that the dimension of this null space of A is equals to 1 because he says that I have one non-zero solution and multiples of it. All right, once you have figured that out, then what? So what is he asking again? He's asking, will the system have a solution for every possible choice of constant on the right-hand side? He's saying that if I plug in any right-hand side, would I find a x such that ax will be equals to b? That's a solution. If ax is not equals to b, then there's no solution. Okay. All right. So guys, if we go back to our first tutorial and second tutorial, we have already figured out that to have a solution, the columns of A, when performed with linear combinations of these, must be equals to B. So I write it down for you. So I'm going to write the columns as A1, A2 up to A6. The linear combinations of columns of A we're talking about is x1 times A1 plus x2 times A2 plus x6 times A6. And somehow all of them, when add up together, I found the correct x will be B1, B2, B6, B5. For any B. So if you reach this point, then you understand that he's asking you, does the column space, does B fall into the column space of A? That is the question. So he went one big round to ask you this question. And then maybe then you say, it's okay, fine. He have already told us there is one free variable in this whole system of equation. Therefore, the rank of the matrix A is 5. The dimension that we are interested in B, the B belongs to R5. Therefore, B must lie in the column space of A. And the answer is yes. For every possible constant, we can find a solution. Now, so Nico and Nguyen, did I answer your question? Or if you want to prefer something more concrete, I'm going to give you to you now. And then, okay, let's find some. Let's do something more concrete. Okay, maybe just now was very abstract. Let us have an A that is a 2 by 3 matrix, and a B, therefore it is in R2. Now let this A have rank 2, very similar to the problem we have here. Let A be very simple such that I have 1, 0, 1, 0, 1, 1. And therefore now I have the x's as x1, x2, and x3. And then I have b1, b2. So this problem is very close to this problem. Okay? All right, so let's figure out what we can find. In fact, this matrix is trivial because he has already shown you that the matrix A has 2 pivots, so it is rank 2. And then because it has one free variable, then I definitely know that the null space is not has one vector. Okay, let's figure this out and let's continue to do this problem. So I'm going to expand this matrix vector multiplication to be x1 plus x3 is equals to, let my right hand side be 0 first, okay guys? So I'm going to set my right hand side to be 0 first, the homogeneous problem. And the second equation is x2 plus x3 is also equals to 0. So this implies x1 equals to minus x3, imply x2 equals to minus x3. Now, if I want to represent my solution, x1, x2, x3, what am I doing? I realize that I look at these two and I will write x3, and the answer is, this is minus 1, this is minus 1, this is 1. So the solution of ax equals to 0 for this problem is this vector. I can put this solution with any constant, and the solution will be ax equals to 0. So far, okay? Now, then, once you have that, then if the right-hand side is equals to b1, b2, what do? Actually, you can study this, and we'll put it down here. And now we'll write the same thing, 1, 0, 1, 0, 1, 1, x1, x2, x3. Now, if the right-hand side is equals to b1, b2, what do you think I would choose x1 and x2 be? Isn't it? So the solution for the above is actually x is equals to x1, x2, x3 is equals to b1, b2 plus the homogeneous solution, any alpha times minus 1, minus 1, 1. So this is it. So it shows that my solution is aligned with this parametric form. Now, but what has it revealed is that there is no problem to get the right hand side, because in fact I just stick the right hand side b1, b2, 0 as x1, x2, x3, and I would get the right hand side for any b's. So the solution is that for any b's on the right hand side, I will be able to find, and not only that, I have an infinite solution because my null space is not 0. Okay, so this is the other way to look at it concretely. So question 14 is actually not so easy. All right. Now, if you have a problem with that, then you realize that I have already written it down, and then you can see it in my solution. So if you go to my solution here, under this guy, you can take the scanned copy of the solution, which I have worked out. Okay, I'm giving this example as well. All right. U is a column vector, so is V. And typically you do U transpose V because you're talking about 1 by 3 and 3 by 1, and you'll get a scalar 1 by 1. Right, but today we are not interested in the dot product, which is U transpose V. We're interested in UV transpose, which is a column vector, 2 minus 3, 5, and a row vector, A, B, C. So this guy is 3 by 1, and this guy is 1 by 3. And interestingly, we can still perform this because this guy agree. So we'll get a 3 by 3 matrix. So this guy is called the outer product. We are taking the outer product of two column vector. Now the outer product is interesting because basically what happened is that you put down the columns and A is multiplying by them, that's all. And then the second column is still 2 minus 3, 5. And you're now multiplying by the second scalar in the row vector. And then, so far okay? So the outer product is nothing but this very concrete operation. Now, what you will also realize is that once you have fixed A and B, isn't this dependent? Everything is dependent. The first column, second column, and third columns are scalar multiples of each other. So is the row, right? Once you have fixed A, B, C, then the first row and the second row and the third row are also scalar multiplication of each other. Therefore, immediately you will say that this is the rank 1 matrix. Now you look at this question carefully. He says that verify that this guy is rank 1 or less than 1, means 0. The rank cannot be 0, cannot be negative. So then you say, in what case would the matrix have rank 0? In the case when a matrix has rank 0 only when all entries of the matrix is equals to 0. And is this possible? Yes, of course. When we have A, B, C is equals to 0, then the whole matrix will be reduced to, and therefore, yes, it is possible. It'll be rank 1 or 0, and it'll be rank 0 only when all the elements of A, B, C is equals to 0. That's it. So that's all for the few questions. And I'm going to pause now. I'm going to stop the recording actually.